Hi, thanks for joining me. Last week I made a magic maths video in which I showed you a magic trick and then showed you how it was done using maths. So it was a maths-based magic trick, and then I explained it using some cool maths and modular arithmetic and things like that. So I'll leave a link for that in the description below. If you haven't checked it out, check it out after you've watched this one. I'm continuing with the theme of magic and maths today, and I'm going to be showing you a David Copperfield trick. I'll explain the trick, show you how it's done or how David Copperfield could have done it, and then we're going to ask a more sort of general mathematical question because, again, this is a math channel, not a magic channel, so we're going to be sort of focusing on the math side of things as well. But of course, it's a pretty cool trick, and yeah, something you can do and try and fool your friends with. Anyway, let me explain the trick, and I've written it in a more mathematical setting than David Copperfield would have performed it in. I've got an n here, whereas obviously David Copperfield would have used an actual number. Anyway, we've got these cards labelled 1, 2, 3, so on, all the way up to n minus 1 and n. Here, n is just some positive integer, which is at least 3. Okay, and we've also got these hats here, hat 1, hat 2, and hat 3. Now, David Copperfield, the magician, takes these cards here and places them inside the hats 1, 2, and 3 in what we're going to call a special distribution. And I'll come to that in just a second, but he places these cards according to some special distribution. So some will go in hat 1, some will go in hat 2, and some will go in hat 3. In particular, none of the hats are left empty, so each hat has at least one card in. Then David Copperfield turns to the spectators and chooses one at random, brings a spectator on stage. David Copperfield turns his back, and then he gets the spectator to choose two particular hats, and he doesn't tell David Copperfield what they are. So David Copperfield isn't facing the hats, he's looking away, and say the spectator chooses hat 1 and hat 3. Then David Copperfield says, reach in and take one card from each hat. So the spectator will choose one card from hat 1 and one card from hat 3. Let's say the spectator chooses 2 from hat 1 and the card labelled 7 from hat 3. Then David Copperfield says, shout out the sum of those two cards. So in this case, he's chosen the card labelled 2 from hat 1 and the card labelled 7 from hat 3. So he's going to shout out 9. 2 plus 7 is 9. And then from that, David Copperfield can go, right, the one hat that you didn't choose was hat 2. And of course, he'd be correct. And now this distribution, this special distribution, i.e. the way that David Copperfield puts the hats into the cards originally, guarantees that he'll always be able to essentially do the magic trick, i.e. give the correct answer. There'll never be any ambiguity as to which hat was not chosen, or equivalently, which two hats were chosen. Okay, and we want to know, firstly, can we find a special distribution? That's sort of one, kind of the somewhat more basic answer, and perhaps it's a seemingly uninteresting magic trick, but maths-wise, there's so much interesting maths involved. And secondly, the more interesting problem is, how many special distributions are there? Okay, so if you want to have a go at this problem, or just trying to work out, can you find a special distribution, pause the video now and give it a go for yourself. And I'm going to jump into finding a special distribution and then asking how many are there. Okay, so the first type of special distribution I'm going to talk about is what I'm going to call the modulo distribution. So what is this? David Copperfield places the cards into the hats according to their residues modulo 3. So we've got hats 1, 2, and 3 here, and what he's going to do is place the cards in, and all the cards with the same residue mod 3 that he's going to put in the same hat. Now, firstly, the hat numbers don't really matter. You know, if I switch hats 3 and 2, it's not going to really affect anything. So in fact, this actually corresponds to 6 special distributions, each depending on the permutations of the hats 1, 2, and 3. But basically, if we just assume this is hat 1, this is hat 2, and this is hat 3, we're going to put card 1 in here, for example, card 4 in here, card 7 in here, because those are all congruent to 1, mod 3. In this one, we're going to put card 2, card 5, card 8, and so on. I should put, and so on up to n. And in this one, we're going to put card 3, card 6, so all the multiples of 3 in this one, and so on. Basically, all the ones that are same mod 3, like so. And now, why does this work? How we guaranteed that David Copperfield can perform the trick? And well, we can just look at it case by case. So if the spectator chooses one card from here and one card from here, we don't know what the cards are, but David Copperfield will look at the sum, and in particular will look at it mod 3. So if the spectator's chosen one from here and one from here, so hats 1 and 2, the sum he's going to give is going to be congruent to 1 plus 2 mod 3, which is congruent to, is going to lead to something that's congruent to 3 mod 3. We usually write 0 mod 3, but that's 3 corresponding to that hat which isn't chosen. So if the spectator chooses something that's congruent, if the spectator shouts a number which is congruent to 3 mod 3, then David Copperfield knows that the remaining unchosen hat is 3. Great. What if the spectator chooses cards from 2 and 3? Well, then that's going to correspond to, if we add them up, something mod 2 plus something mod 3 is just going to sum to something mod 2 mod 3. So if David Copperfield hears a number 2, then he knows that the hat that wasn't chosen was 1. And now if if the spectator chooses 1 and 3, so the remaining pair of hats, let me just write it here, then that's going to correspond to a sum of 1 mod 3 plus 3 mod 3 is just 1 mod 3. Mod 3, like so. So if David Copperfield hears 1, then he knows that the hat that wasn't chosen was 2. So all David's got to memorise is if he hears 3, then that means hat 3. If he hears 2, that means hat 1. And if he hears 1, then that means... if he hears a number which is congruent to 3 mod 3, that corresponds to hat 3. If he hears a number which is congruent to 2 mod 3, that corresponds to hat 1. And if he hears a number which is congruent to 1 mod 3, that corresponds to hat 2. Okay, and that sort of shows you one way we can have these sort of cards set up. And of course, as I said, we can permute the hat numbers. It doesn't really matter. It just means David has got to memorize some different sort of ordering of these numbers. But notice 3, 2, and 1 are all distinct. So that means that he can uniquely identify the hat that isn't chosen. Okay, so this is what I'm going to call the modulo distribution. Now let me talk about what I'm going to call the trivial distribution. Okay, so now I'm going to talk about the trivial distribution. So this is kind of a boring way to place the cards into the hats, but it certainly works for the purpose or the mathematical purposes of this trick. So David Copperfield places the card labelled 1 into one hat, so I'm just calling that hat 1. The card N into another hat, which I'm going to call hat 2, and all the remaining cards, i.e. the cards labelled 2, 3, 4, all the way up to N-1, into the final hat. Okay, and again, we have a similar thing where we can permute the sort of numbering of these hats. So again, this kind of corresponds to 6 special distributions. Okay, but let's check that this works. And this one is a little bit easier to see why it works. So the spectator comes along and chooses two hats and picks a card from each of the hats. Let's look at this let's look at if one of them's hat 3 first. So if, say, he chooses hat 1 and then hat 3, then what's we going to get? Well, if we add these two up, 1 plus whatever number is in here, we're going to get some number which is less than or equal to n. Okay, because 1 plus any of the digits in here, even if we choose n-1, the maximum we're going to get is n-1 plus 1, which is n. So this is going to correspond to some number which is less than or equal to n. Okay, what if he chooses 2 and 3? Okay, well then we can clearly see, because this whichever card he chooses from 3 is going to be at least 2, and this one here is n, then their sum is going to be at least n plus 2. So this is going to correspond to a sum which is at least n plus 2. And finally, if it's hat 1 and 2, this is very straightforward. He's going to hear the number n plus 1, like so. And now we see we've kind of got a partition of the natural numbers, or sort of thing. But if he hears a number which is at most n, then he knows that hats 1 and 3 were chosen, so hat 2 was the one that wasn't chosen. If he hears a number which is at least n plus 2, then he knows that hats 2 and 3 were chosen, and thus 1 wasn't chosen. And if he hears a number exactly n plus 1, then he knows that hats 1 and 2 were chosen, and thus hat 3 was unchosen. Okay, so this is another way that David Copperfield could have initially placed the cards into the hats that works. But what's super interesting about this is that these are the only 2 types of distributions: the modulo distribution and the trivial distribution. And of course, that's my claim, but I've got to prove it because this is a math video. I claim that those are the only 2 types of distributions David Copperfield can use in order to guarantee that he can always do this trick, i.e. always deduce which hat wasn't chosen. Let's get stuck into the proof. Okay, so I make the claim that the only special distribution, i.e. the way that David Copperfield can initially distribute the cards amongst the hats, are the modulo distribution and the trivial distribution. And I'm going to prove that by induction. So let's look at the case when n equals 3, i.e. we only have cards 1, 2 and 3. Okay, then notice, because we've got to have each hat having at least 1 card in, then card 1's got to go in one hat, card 2's got to go in its own hat, and card 3 has got to go in its own hat. And we're just going to label up the hats 1, 2, and 3 because remember, we're not really too interested in the permutations of the hat numbers. Okay, cool. But notice that this is both the modulo distribution because card 1 is in the hat with all the other numbers which have the same residue modulo 3 because none of the other cards have 1 mod 3 or mod 1 3 sorry. Same goes for 2 because 1 and 3 aren't 2 mod 3, and same goes for 3 because 2 and 1 aren't congruent to 0 mod 3. Okay, so this is the modulo distribution, but it just so happens to also be the trivial distribution because remember what the trivial distribution said? That said that we put the smallest card, card 1, in its own hat, we put the biggest number in its own hat, or the value of n, so 3, in its own hat, and we place all the other cards in a final hat, which is exactly what we've done here. Okay, so notice that this is both the modulo distribution and the trivial distribution. So this actually satisfies both, which is great, but it's important that they're the same, and we're going to come back to that later. Now, let's proceed by induction. Okay, so now we're going to proceed by induction. So we did the base case. Now what we're going to do is fix some positive integer n, which is at least 3, and assume that the statement holds true for n. That is, that if David Copperfield wants to perform the trick with n cards, the distribution he must use is either a modulo distribution or the trivial distribution. Now David Copperfield has got another performance tomorrow night and he wants to try it with n plus 1 cards. Can he do it? And I claim he can, but again it has to be the modulo distribution or the trivial distribution, and we're going to be using the result on n cards to help us. Okay, so let's split this into cases. Let's first look at case 1, and that's when n plus 1 is alone and 1 is not alone. Okay, so I've put n plus 1 by itself in hat 2. 1 is not alone, so it's with at least one other card here. I've put it in hat 1. Again, the numbering of the hats doesn't really matter. And in hat 3, remember, it can't be empty, so it has at least one card in. We're not too interested in what that card is, but it's got at least one card in. Great. But I claim this is, as I said, this isn't the trivial distribution, and it also isn't the modulo distribution, so I claim that this doesn't work. Okay, let's see why. Well, what we're going to do is look at hat 1 and find its maximum element. So M1 is just going to be the maximum element from hat 1. And similarly, M3 is going to be the maximum element from H3. So the maximum number from H3. Okay, so what do we know about M1? Well, it's at least 2, because we know that 1 is not by itself. So that means there's got to be a card in there which is at least 2. So we know that M1 is at least 2. And we also know that M1 plus M2 is the sum of the maximums from those two. And in fact, we know what that is. We know what an upper bound for that is because we know that n has got to be in one of these hats, and n minus 1 can either be in that same hat or in the other hat. It doesn't really matter, but it's bounded above by n plus n minus 1. Okay, which of course is just 2n minus 1. Okay, what is m1 plus m2 bounded below by? Okay, and this is an interesting question. Now you might think it's, I don't know what you might think it is, but the answer is it's n plus 2. Okay, why is that the case? Well, because we know that one of these hats, hat 1 or hat 3, must have the card that has n in it, because we know n is not in hat 2. So it's one of them. So one of m1 or m3 is going to be n. We don't know which, but one of them certainly will be n. And then the other one has to be at least 2, because if m1 we know is at least 2, and m3 we also know is at least 2 because 1's not in there and it's non-empty. Okay, so m1 plus m2 is bounded below by n plus 2 and is bounded above by 2n minus 1. This upper bound doesn't really matter too much. It's mainly the lower bound we're interested in. What we're going to do is just call this m1 plus m2. We're just going to label it s. We'll just call m1 plus m2 s. So of course, if David Copperfield hears the spectator shout m1 plus m2 or s, whatever that number is, if he hears the spectator shout s, then for sure the spectator could have chosen the maximum element from 1 and the maximum element from 3. Okay, we don't know what they are, but certainly it could just happen by chance that that's what the spectator has chosen. And the spectator will shout out S, and that's what David Copperfield will hear. So he'll think it's those two cards. However, it may not be those cards, and the reason for that is the spectator could have also chosen n plus 1, and then whatever S minus n plus 1 is. Now, this is where this inequality comes into play, because we know S is at least n plus 2, so that means that S minus n plus 1, whatever it is is at least 1, and also we know that it's, and this is where the upper bound comes into play, it's certainly going to be less than, or at most n, so it's going to be in one of these two hats. So if the spectator just so happens to choose n plus 1, and then choose whatever s minus n plus 1 is, we don't really know what it is, but it could be in hat 1 or it could be in hat 3, then David Copperfield won't know, because they both sum to s. And that's where the issue comes in, because they're coming from two different hats. If the spectator chooses M1 and M2, that's coming from hat 1 and hat 3. So David Copperfield might think to shout hat 2 is the one that's not chosen. However, if the spectator just so happens to choose N1 from there, and then wherever S minus N plus 1 is, we don't know, then that means that the hat that isn't chosen is either 1 or 3, but in particular it's not 2. Okay, so David Copperfield will be stumped, he won't know what to do, and he'll break down crying, because this won't work. So, because this isn't the trivial distribution or the modulo distribution, we're still good. We now need to check the other cases, i.e. when n plus 1 is not alone and when 1 is alone, and that sort of stuff. Let me clear the whiteboard and we'll continue. Okay, so I claim that the card that says n plus 1 on it must go in the corresponding hat. So whatever n plus 1 is mod 3, it will go in that hat. And the reason for that is, if it doesn't, then we can find two sets of cards coming from different sets of hats which add up to the same number. And thus David Copperfield won't know, won't be able to guarantee that he chooses the correct hat. Okay, so suppose, without loss of generality, let's say that n is congruent to 1 mod 3. And you can apply the exact same argument if n is 2 or if it's 0 mod 3. Okay, so if n is congruent to 1 mod 3, then we know that n minus 2 is going to be congruent to minus 1 mod 3, so it's going to be congruent to 2 mod 3. Is that right? Yeah, that's right. That's right, yeah. Just have to check that. N minus 2 then is congruent to 2 mod 3. Okay, and therefore it will come from hat 2. Is going to come from hat 2. Now we're supposing that, now notice that n plus 1 then is also congruent to 2 mod 3, but we're supposing for contradiction that it doesn't go in hat 2. But then n minus 2 plus n minus 1 n plus 1 equals 2n minus 1. But because we're assuming that this doesn't go in H2, where it should, for the modulo distribution, we're supposing it doesn't go in there, then that means it doesn't go in H2, so we can take n minus 2 from hat 2 and then n plus 1 from whichever hat it goes into, and it's going to sum to 2n minus 1. Cool. But then notice we could also take the numbers n and n minus 1, and that would sum to 2n minus 1. And n is coming from hat 1, and n minus 1 is coming from hat 3. So if David Copperfield hears 2n minus 1, he might go, this one is coming from there, n minus 1 is coming from there. So that means that the remaining hat is hat 2. He'd shout hat 2, the one that isn't chosen. But if he hears this, or he might think this, n minus 2 and n plus 1, or n minus 2, is coming from hat 2, because it's congruent to 2 mod 3, and then n plus 1 is either from 1 or 3, you don't really know. But then, in particular, the hat he's going to shout out is going to be 1 or 3, and in particular, it's not H2. So that leads to a contradiction, or David Copperfield doesn't know what to do. So I hope that makes sense. So that's kind of the first case when we take out n plus 1, what we're left with is a modulo distribution. Now let's look at what happens when we take out card n plus 1 and we're left with a trivial distribution. Okay, so now what we're going to do is when we take out the card n plus 1, suppose we're left with a trivial distribution, where do we put this card n plus 1? And I claim it's impossible to place it anywhere. Why is that the case? Well, suppose when we try and put it back, we put n plus 1 and 1 in different hats. Doesn't matter which, but suppose n plus 1 is in hat 2 or hat 3. Well, then that means that, as I'm saying, 1 and n plus 1 are in different hats. So then I could potentially choose 1 and n plus 1. Or the spectator could potentially choose 1 and n plus 1. But also they could choose 2 from here and n from here. So that will give us this thing here. And then these both sum to n plus 2. But clearly, oopsie, daisy, this one here involves hat number 1 and this one doesn't. So David Copperfield won't be able to distinguish. Cool. What if card n plus 1 and 1 are in the same hat? Okay, so if hat n plus 1 and card number n plus 1 and 1 are in the same hat. Now, firstly, perhaps I should have mentioned this earlier, is we can assume at this step that n is at least 4. Why can we do that? Well, remember I said that if n is 3, the trivial distribution is actually identical to the modulo distribution. Okay, so in the modulo distribution case, we've already dealt with that. We just dealt with that on the previous whiteboard. So that's already dealt with. So it just so happens that the trivial distribution is the same as the modulo distribution when n is 3. So we can assume here, because we're looking at trivial distributions, that n is at least 4, because we've already dealt with all the modulo distribution cases. Okay, so we're assuming that n is at least 4, and now we just looked at when n plus 1 and 1 are in different hats. Now let's look at when they're in the same hat. So if n plus 1, we plonk into that hat there, well then we can choose, what can we choose? We can choose 3 and n. So 3 from this guy here and n from this guy. And we know that 3 lives in this hat because we know that n is at least 4. We're assuming n is at least 4. So certainly n minus 1 will be at least 3. So we choose 3 from this hat and n from that hat. That of course sums to n plus 3. But we can also now choose n plus 1 from this hat and 2 from this hat. And that also gives us n plus 3. And David Copperfield won't be able to distinguish. This one here involves a card from hat 1, and this one doesn't. So that David Copperfield is going to have some issues there. Okay, and that concludes our proof. We've shown by induction that it must either be the modulo distribution or the trivial distribution that David Copperfield uses. This has been a very long video, so I apologise, a lot longer than my standard videos, but I think this is super cool and super interesting. I hope you found it interesting and fun as well. A pretty cool magic trick. If you want to try this magic trick, it doesn't seem like the most impressive, especially with the trivial distribution, but if you tried it with the modulo distribution, I'm sure it will fool at least some non-mathematicians, but if you showed it to a mathematician, they might not be as impressed. Nonetheless, if you do try it, let me know how it goes in the comments. I hope you have enjoyed this video. I'm going to stop waffling. Thanks for watching. I'll catch you in the next one. Have a great day.